Okay, so the next little piece, or really set of pieces in this case, that it's just going to be quickly mentioned in lectures, and you're just going to hear the phrase over and over again. It might seem like something kind of complicated, like all the stuff in this video, something mysterious. It's just a mysterious piece that works, and it's probably too complicated to understand or whatever if you just hear that phrase over and over again. And it's really not. This one is especially simple. And as far as overcomplicating it, when our class lecture goes over logic, I'm going to talk about logic in depth and talk about math class and English class and philosophy class, and I'm going to throw out some Latin phrases like modus tollens, modus ponens, and I might try to explain what those Latin phrases mean, denying the consequence, that sort of thing. It's and how the logic works out as the thousands of years of history has built up to logic, and it's going to seem super complicated. And then we're just going to mention these names. It's like, okay, we have these things called logic gates. Okay, that's good. Probably going to seem really complicated there, but it's a very simple electrical piece. Actually, you may have noticed I'm not making these videos these videos aren't necessarily being made in order, so I don't know if it's mentioned at this point or not. But all electrical pieces are simple, right? If you think about it, when we write this, we've talked about before with our binary stuff, we use ones and zeros because they're quick and easy to write. But any binary state, true, false, yes, no, different ways we can think about it depending on the situation. But we usually write a 1 and a 0 because they're quick and easy to write. And the point I was getting to is there's only two symbols. We can't do complicated things and then represent it with only two symbols. So all of the electrical stuff is easy. That's why we call it low level. That's the low level. We represent it with two symbols, and we can't represent complicated things with only two symbols. So all the electrical stuff is simple, and when the class lecture talks for length about logic and throws out Latin phrases and what logic means in an English class versus what logic means in a math class, and then tries to tie those together for what computer programmers need to know about logic, it's going to seem complicated, and then this word's just going to get thrown in there. But our logic gates are ways to combine signals or alter signals is basically what they are. So let's take a look at a few of them. I'm going to draw some diagrams on the board, and then we'll look at a circuit with actual switches, which obviously I'm going to be flipping the switches with my fingers so you can see what's going on and know that it really is just a switch. But in the computer, we use transistors, which that video may have been before this one in the playlist or after this one in the playlist. But there's a video about transistors as well, kind of breaking down how those work as switches. But yeah, so let's get started into these with our first basic one. A NOT gate. Or if we're referring to the electrical components, technically the electrical version is called an inverter. So it just inverts the signal. I'm filming this at night, so I always have to be careful. My light source is in a different place than it is in the day. The light bulb's over there and the windows are over there, so I always forget about my shadow sometimes. So the electrical piece, we call it an inverter. Typically, when we're talking about computer stuff, we just say a NOT gate. I should write that in capital letters. The NOT. And our truth table is very simple for this. So we have our input and our output. So our input can either be on or off, right? Either off or it's on. And the output is what it's not. It inverts it. So if our input is off, our output is on. And if our input is on, our output is off. It's kind of all there is to it. It's included as well, so our typical symbol for this, if you see in a circuit diagram, looks like a triangle with a little dot afterwards. So when you see that symbol in a schematic, that means a NOT gate. And to how this works, there's a small bit of electricity, small bit about electricity you have to know. And you may have probably heard it before, the common phrase, current takes the path of least resistance. That's basically all you need to know. And whenever we form a circuit, we have the voltage coming from somewhere, applied from somewhere, and it's always trying to get to ground, is how we phrase that. There's a technicality there. I'm gonna use conventional mode. I'm going to refer to everything conventionally, which is that it goes from the positive to the negative. So our electricity is always starting at some source and trying to get to ground is what's going on. So we can take advantage of that fact. So say we have some source. So we have some voltage source coming in. For the example here, I just plugged up to a 5 volt supply I had. We have 5 volts applied somewhere, and it's going to come through and then try to get out. I'm going to draw it like this. And over here, some sort of load. For the example, here in a moment when we go over and look at that, I just have an LED there, but we're doing something with the electricity, which is going to produce resistance. So we're going to create resistance over here of whatever we're doing with the electricity. So this is our actual output. So that's our output. But the thing I just said, current takes the path of least resistance. So when we do stuff with electricity, there's going to be resistance involved. So what we could also do is form a little junction here and then come down through a switch. And have our ground here. So when the switch is open, which is off, you can see from the picture the little thing's the wire's not touching. The switch is open, the current can't flow through here and get to ground. So the only thing the electricity can do is flow through our load, which has a bunch of resistance. But if we go and close this switch, well, then there's no resistance on the way back to ground, and current takes the path of least resistance. So if there's resistance on our load and no resistance through the switch to get to ground, the current is definitely going to go through the switch and get to ground and not go to the load. So that's kind of how a NOT gate works. We'll step over here and look at it in an actual circuit with the switch so you can see a light coming on and off. And so here is that wired up onto a circuit. First off, I guess I should point out these switches that I used for this didn't have labels that showed up very well on the video, so I went ahead and wrote the stickers so you can see which way on and off is. So right now, the switch is off and our output is on. So I have a power supply here, and so anything connected to this top row here is going to be our source voltage. And then the bottom row way down here, that's our ground way down here. So, like we saw in the picture, we have our, in this case, 5 volts is going in, comes through this resistor. That's just to adjust the current, because I kept blowing a fuse when I first tried this. So the voltage is going to come through here,
and then it hits this little junction of wires. So one of them obviously is the output. It's the voltage comes in, goes through this wire down to the LED, then drops to ground. So the output is on right now. But from this junction, there's also an alternative. The electricity could flow over to the switch. And right now the switch is off, so it can't get back to ground this way. But when I turn the switch on, you'll notice now that the switch is on, this becomes the better route for the electricity to flow back to ground. And that's how an inverter works, the NOT gate. When our switch is on, the output is off. And when our switch is off, the output is on. And that's all it takes. It's just the switch provides a better route for the current in the circuit to get to ground. And then obviously in a machine, we're not going to manually reach in and flip those switches. We just use a transistor or a MOSFET, which is a type of transistor, or maybe even a relay, something electromechanical so that the machine flips its own switches. And we can wire it up that same way so that when our switch is on, our output is off, and when our switch is off, the output is on. So flip that one more time. So if I turn the switch on, the output went off. And if I turn the switch off, the output came on. So that's how a NOT gate works. It's just the switch provides a better route for the electricity.
So next up is an AND gate. And just like we use the word when we're speaking in English, AND is inclusive. So we just do the truth table real quick. We call a couple of inputs A and B, because it's AND, so we need two inputs. And then we have an output. And our inputs can either be on or off again. So I'll do off, on, off, on, off, on. So that's all the combinations we could have, right? They could both be off, one or the other could be on, or they could both be on. And is inclusive. So if they're both off, well, obviously the output's going to be off. And if one is on and one is off, then the result is going to be off. Likewise, with a switch on that, off, on results off and on results in off. On and off results in off. Only on and on will give us an output that's on. And to make this even simpler than the NOT gate. So we have our voltage source, just applying a few volts, and again in the example, it's just going to be 5 volts there. That's going to come over, and I'll put it over here. Over here is our load. I'll draw that a moment ago. And between the voltage source and the load, we'll just put a couple switches. One switch, and a second switch. So you can almost see from the picture, the way we draw a switch in a schematic, the current can't flow through there because while the switch is open. So the only way the current can get from the voltage to the load is if both switches are turned on. So let's go take a look at that real quick.
And so here's what that looks like wired up as a circuit. In some ways, this one almost might be easier to understand. To understand a NOT gate, you had to at least know the electricity is always trying to find the shortest route to ground. Current takes the path of least resistance is a phrase you may have heard before. You had to at least know that. But for an AND gate, if you've ever used a light switch, it probably makes sense. So our voltage comes into the first switch, which again, the labels didn't show up, so I have the off and on stickers here. So when the switches are this way, it's off. When the switches are this way, it's on. So the voltage goes to the first switch. So, and then the output from the first switch goes to the second switch, and then the output of the second switch turns the light on. So obviously if they're both off, they're not going to be on. But if the first one's on and the second one's off, well, we have an AND situation. So it still can't flow through there. And same thing vice versa. If the first one's off and the second one's on, well, the voltage can't get past this switch. Only when they're both on, so that's our AND. This switch is on and this switch is on. And once again, if we have some sort of electromechanical switch, or probably electrical switch, not necessarily electromechanical till we get to big things, if we have the machine is flipping its own switches, that can happen very, very rapidly. And the same thing, the electricity can't flow through here. We can't get any current flowing unless both switches are on. And that's how an AND gate works.
So when I went to erase the board to get ready for the next scene, I noticed I forgot to write the symbol. So schematically, when we draw an AND gate, it's going to look like that. Sort of a little half of an egg shape. 2 lines coming in, 1 going out. That's what this symbol looks like for an AND gate. So when you see that on a schematic, that means one of these type of gates. I forgot to draw it, so I forgot to mention it briefly. So we move on to the last one that we're going to look at here, which is an OR gate. So we have 2 signals, and OR doesn't have to be inclusive, one or the other, right? Picking a place to go get food, hamburgers or tacos. It doesn't matter. Either one's fine, right? As long as there's food, that sort of thing. Or doesn't have to be inclusive. So if we look at the truth table for it, I have 2 inputs and an output. And again, the only combinations we could have are on and off. So off, off, on, off, on, off, on. So obviously if they're both off, there's no way we can get on from 2 offs. But either one will be fine, right? So if the first one's off and the second one's on, our output's going to be on. And vice versa. If the first one's off, or first one's on and the second one's off, then our output's going to be on. And if they're both on, then our output's going to be on. So if basically an OR is when anything's on. So with an AND gate, it's only on when both inputs are on. But an OR gate is on when any of our inputs are on. And the schematic for that, I can't draw this one quite as well. Looks something like this. We have a couple lines coming in, and then 1 line going out. And to draw it's a fairly simple circuit to set up. So we have our voltage, and then we give it 2 paths to go through. On one of the paths, we'll put a switch, then we'll come back around. The other path, kind of the same thing. Put a little switch here, come back around and rejoin this, and then head over to our load. So if either switch is closed, if we turn this switch on, then our current can flow that way to get to the load. If we turn this switch on, current can flow that way to the load. So if either switch is on, the current has a route to get through from the voltage source to the load. Let's go look at it in a circuit.
Okay, and here's what that OR gate is going to look like in this circuit. So our voltage is over here on this red line. It can come through the first switch, then through this white wire to get to the output, or the light bulb, the LED in this case. Or the voltage can come through this red line over here and through the second switch and reach the light. So in this case, obviously, if both of them are off, the output's going to be off. But if we turn the second switch on and the first switch off, our output's going to be on. And vice versa. If the first switch is on and the second switch is off, then our output's on. And obviously, then it's an OR gate, so if both switches are on, our output's on. And that's how an OR gate works, only typically we would use transistors or something electrical so that the machine is flipping its own switches. It can switch them a whole lot quicker, but the point of these videos is it's not some mysterious, complicated thing that makes an OR gate. As you can see here, it's just a choice of switches. Both switches will turn on the light. So if either switch gets turned on, then our LED gets turned on. And that's all there is to an OR gate. It's not some super mysterious thing.
Okay, so hopefully that helped to remove some of the mystery and mystique around what a logic gate is, instead of just hearing that word in programming class and not knowing what it was. You can see it's just the way that we can hook up switches to get what we want. And then we have the machine flip its own switch, which it can do very, very rapidly. So we can do that lots and lots and lots of times and get the results we want out of a simple combination of switches. And then we can build up others. So obviously we can combine the nots and ands anytime we want. And that's so common, we have a symbol for it. Might as well draw that. It's like an AND gate, and we add a little dot. Sometimes you'll see the dots over on this side, but some combination of the little dot from the AND gate on the AND symbol for a not AND or NAND gate. Same thing with an OR. We'll add the gate, and then we'll add the little dot in to indicate that it's a not OR gate or an OR gate. And I considered including XOR, exclusive OR, so it's like an OR gate where it's one or the other, but only one or the other. So an XOR, might as well draw the symbol here since I mentioned it. It looks like an OR gate, but we'll have an extra little line back here. And it's exclusively OR. It's one or the other, but not both. And the reason I left it off is because even in the simplest form, we build it up from a not, an and, an OR. Actually, if you're curious how that works, we go through an OR gate and an AND gate both, and then the AND gate triggers an inverter, a not gate, to turn everything off. So if both lines are on, then the circuit gets turned off. So it's built up of the previous ones. So it's not really one of the three basic ones. That's why I excluded that from the video. But it's almost a basic one. But we can put those in different combinations and build up the logic of what's going to happen when the electricity starts flowing through a circuit based off how those switches go. It's not some big mysterious piece. Hopefully that cleared that up some and wasn't too confusing.